I am very happy to welcome you again to this module. The module title is Statement of Fundamental Theorem of Arithmetic and Principle of Mathematical Induction. In this section, we introduce Statement of Fundamental Theorem of Arithmetic, which justifies prime numbers or building blocks of positive integers, and then we learn a method called Principle of Mathematical Induction, which helps us to understand how to prove statements involving natural numbers in an easiest way. The statement of fundamental theorem, that is what we are going to see now. Fundamental theorem of arithmetic helps us to represent any integer greater than 1 as a product of primes in unique way. This in fact makes the assertion that prime numbers are building blocks of positive integer. That is, for example, 8 can be written as 2 multiplied by 2 multiplied by 2, that is the product of prime numbers, and 6 can be written as 3 multiplied by 2. 5 is equal to 5 because 5 itself is a prime number. Before moving to the theorem, we want to prove certain results which helps us for our further proof. First, we shall prove this proposition. If P is a prime such that P divides AB, where A and B are integers, then P divides A or P divides B. We shall prove this now. If P divides A, then there is nothing to prove, right? So, suppose if P does not divide A, then we have to prove that P divides B. So, if P does not divide A, then the GCD of P comma A is equal to 1. Since the GCD of P comma A is equal to 1, there exist integers m and n such that 1 can be written as, that is the GCD can be written as the linear combination of P and A, that is 1 is equal to MP plus NA. Multiplying this equation by B, we get B is equal to B multiplied by 1. In the place of 1, I can write MP plus NA, that is B is equal to B multiplied by MP plus NA, that is equal to BMP plus BNA. Since P divides AB and P divides BP, it follows that P divides PMB, that is B multiplied by MP plus BNA, which is equivalent to saying P divides B. So, that is we have proved the proposition. Moving to the next proposition, if P divides A1, A2, etc. AN, that is the product of all of them, where A1, A2, etc. AN are positive integers, then P divides AI for some I where I varies from 1 to n, that is if P divides product of all the integers, P should at least divide at least one AI, one element for that matter. So, we shall prove the proposition now. Now, suppose the prime P divides the product A1, A2, etc. AN of n integers. By the previous proposition, we can have P divides A1 or P divides A2, A3, etc. AN. So, in the product, I have considered A1 separately and all of them together separately. So, in the later case, applying the proposition again, we have P divides A2 or P divides A3, etc. up to n. If you continue to apply it for n minus 1 times, we get P divides A1 or P divides A2 or etc. P divides AN, that is P divides AI, where I varies from 1 to n, that is 1 less than or equal to I less than or equal to n. So, now we shall see the fundamental theorem of arithmetic. Every integer n greater than 1 can be written as n is equal to P1 multiplied by P2 etc. multiplied by Pk for unique primes P1, P2 etc. Pk. Equivalently, every integer n greater than 1 can be written as n is equal to q1 power alpha 1, q2 power alpha 2 etc. qn or qs power as. This is called as prime decomposition of n. As the product of powers of distinct prime numbers q1, q2 etc. qs. So, that is we have expressed n as a power of distinct primes. These primes and the exponents a alpha 1, alpha 2 etc. alpha s are always unique. So, this is the statement of the fundamental theorem of arithmetic. Now, we shall prove this statement. Okay. So, if the result is false, then the set of integers n greater than 1 which cannot be written as the product of primes is non-empty, and so by the well ordering principle contains at least a least element, that is m. Since this number is not a prime number, m can be written as a multiplied by b, where 1 less than a less than m and 1 less than b less than m. Then by minimality of m, because m is the least element, no, each of a and b is the product of primes, hence so m is also a product of prime, that is the contradiction. Now we have to prove the uniqueness of it, that is n greater than 1 can be factored in one way as the product of primes. We can assume that n can be represented in two different ways. So we have to prove the uniqueness of it, therefore we are going to assume n can be decomposed in two different ways, that is n is equal to p1 multiplied by p2 etc. multiplied by pk, and the same n can be written as q1 multiplied by q2 etc. multiplied by qk, where pi's and qi's are all primes. So we have to prove the uniqueness. We suppose n can be written as in two different ways, that is n is equal to p1 p2 etc. up to pk, and the same n is written as q1 q2 etc. up to qk, where pi's and qi's are all primes. Cancelling equal factors on each side of the equation, we get p1 multiplied by p2 etc. pk is equal to q2 q1 q2 etc. up to qk. So this is the equation. We have to cancel on each side. We either have an equation of which says that the product of this prime is 1, which is not possible, or another equation where none of the primes pa is among the primes qi. Then since p1 divides p1 multiplied by p2 etc. pk, p1 divides p1, therefore p1 will definitely divide the multiple of p1, that is p1 will divide p1 multiplied by p2 etc. multiplied by pk. It follows that p1 divide q1 q2 etc. qk, because q1 q2 etc. qk is equal to p1 p2 etc. pk. By the above proposition, we can say that pi divides qj, because p1 divides all the product, therefore p1 should divide at least one of them, right? Therefore p1 should divide qj for some j. So or for that matter, instead of p1 you can consider pi also. So since both pi and qj are primes, this forces pi to be equal to qj, that is the contradiction. Therefore the representation is unique. We have assumed in two different ways, now the representation becomes unique. This decomposition n is equal to q1 power alpha 1 q2 power alpha 2 etc. qs power as alpha s is called the prime decomposition of n. For example, the prime decomposition of 120 is 2 power 3 multiplied by 3 multiplied by 5. So this prime decomposition of a number will be helpful in proving so many important results. Next, we shall see a definition. The prime factors or prime divisors of an integer n greater than 1 are the prime numbers which divides n. The multiplicity of a prime divisor p of n is the largest number alpha such that p power alpha divides n. And then we shall see about canonical decomposition. The canonical decomposition of a positive integer n is of the form n is equal to p1 power alpha 1, p2 power alpha 2 etc. pk power alpha k, where p1, p2 etc. pk are unique primes with p1 less than p2 less than etc. less than pk, and each exponent alpha I is a positive integer. So we shall see an example now. So we are going to find the canonical decomposition of 2520. Beginning with the smallest prime 2, since 2 divides 2520, 2520 can be written as 2 multiplied by 1260. Now 2 is a factor of 1260, and so 2520 can be again rewritten as 2 multiplied by 2 multiplied by 630, and 2 divides 630 again. Therefore 2520 can be written as 2 multiplied by 2 multiplied by 2 multiplied by 315. Now 2 doesn't divide 315, but 3 does. So 2520 can be written as 2 multiplied by 2 multiplied by 2 multiplied by 3 multiplied by 105. 3 is a factor of 105 also. Therefore, 2520 can be written as 2 power 3 multiplied by 3 power 2 multiplied by 35. Continuing in this way, we at last get 2520 is equivalent to 2 cube multiplied by 3 square multiplied by 5 multiplied by 7. That is our desired canonical decomposition. We shall see an alternative method for the canonical decomposition. Notice that 2520 can be written as a product of 40 and 63. Since none of the factors are primes, split them again, that is 40 can be written as 4 multiplied by 10 and 63 can be written as 7 multiplied by 9. And so we have 2520 to be equivalent to 4 multiplied by 10 multiplied by 7 multiplied by 9. Since 4, 10 and 9 are composites, split each of them. You have 2520 to be equivalent to 2 multiplied by 2, 2 multiplied by 5, 7, 3 multiplied by 3. Now all the factors are primes. So the procedure stops here. Rearranging them yields the canonical decomposition as 2520 to be equivalent to 2 cube multiplied by 3 square multiplied by 5 multiplied by 7. In either way you have the same decomposition, that is unique canonical decomposition. Next, we shall talk about one of the most used principle in proof is principle of mathematical induction. In this section, we are going to learn about mathematical induction. It is one of the easiest way of proving the statements related to natural numbers. Here is an example which serves as a good model for mathematical induction. Suppose if you queue 100 square tiles and want to let all of them fall by allowing first square tile to fall, how would you queue it? The best idea is to queue such that when the very first tile topples, it will lean against the second tile and make it fall. Ensure that each tile will make a tile fall. If condition 1 and condition 2 are satisfied, then all the tiles will fall, right? We know that set of natural numbers, which is a subset of real numbers, holds the ordered property. Suppose we wish to find the formula for the sum of positive integers 1, 2, 3, etc. n, that is a formula which give the value of sum of n natural numbers. For example, find the sum of first 3 natural numbers. Here n is 3 and we have to find a formula which will give the value of 1 plus 2 plus 3, and we already believe that the formula 1 plus 2 plus 3 etc. plus etc. n is equal to n multiplied by n plus 1 by 2 is the correct one. How we got the formula, or how can we prove that this is the formula for finding the sum of n natural numbers? We have to have a concrete proof, right? We cannot prove this formula by finding the sum of all n natural numbers. What we are going to do is, we will prove this for a particular natural number n, and the formula will automatically follows then for the next positive integer and next indefinitely. The example discussed so far made assertions about infinitely many consecutive integers. In this case, we adopted the following strategy. First one, verify that there is a solution for the smallest integer. Show how a solution for one integer leads to a solution for the next. This method is actually produced by mathematical induction, which can be stated as follows. The principle of mathematical induction. The statement follows here. Let P of n be a statement where n is the integer satisfying the following condition. The first condition is P of n naught is true for some integer n naught. Second one is, if P of k is true for arbitrary integer k is greater than or equal to n naught, then it is true for the next integer P of k plus 1. Then P of n is true for all integers n greater than or equal to n naught. Property 1 is simply a fact. There may be a situation when a statement is true for n naught is equal to 1, or when a statement is false for n naught is equal to 1. Sometimes the statement is true only for n greater than or equal to 4. So, we set n naught is equal to 4 and we verify the result for P of 4. Property 2 is a conditional one. It does not assert that the statement P of k is true, but it says if P of k is true, then the statement holds for n is equal to k plus 1. This is referred to as the inductive step, and the assumption that the statement is true for n is equal to k, that is P of k is true, is the inductive hypothesis. We shall see an example now. For any integer n greater than or equal to 1, we are going to prove here the sum of the odd integers from 1 to 2n minus 1 is n square. Let us write our P of n as P of n is equal to 1 plus 3 plus etc. plus 2n minus 1. This is equal to n square. That is what we have to prove. First, we are going to prove the basic step, that is, we are going to find P of 1 and P of 1 is equal to 1, that is equal to 1 square. Therefore, the statement is true for n is equal to 1, that is P of 1 is true. The next step is the inductive step. Suppose P of k is true for some positive integer k and we need to prove that P of k plus 1 is true. We have 1 plus 3 plus etc. plus 2k minus 1 is equal to k square. This is our assumption and we are going to prove this for k plus 1. For that, consider 1 plus 3 plus etc. plus 2k minus 1 and then the next statement plus 2 multiplied by k plus 1 minus 1. That is, for the first statement we have proved the value to be, we have assumed the value to be k square. Therefore, that is k square plus 2k plus 1. That is equal to k plus 1 the whole square according to the binomial formula. Therefore, the statement is true for k plus 1 also. Therefore, P of n is true for almost all natural numbers n. Next, we shall see another example. We have to prove here for any natural number n greater than or equal to 1, 1 square plus 2 square plus 3 square plus etc. plus n square is equivalent to n multiplied by n plus 1 multiplied by 2n plus 1, the whole thing divided by 6. So, here also we are going to take P of n to be equivalent to 1 square plus 2 square plus etc. plus n square is equal to n into n plus 1 multiplied by 2n plus 1 divided by 6, and we are going to prove this using mathematical induction. For n is equal to 1, P of 1 is nothing but 1, that is equal, that is 1 square 1, that is equivalent to 1 multiplied by 1 plus 1 multiplied by 2 multiplied by 1 plus 1 divided by 6. In the numerator you have 1 multiplied by 2, that is again multiplied by 3, you have 6 divided by 6, therefore you have 1, which is true. Therefore, the statement is true for n is equal to 1. Now, assume the statement is true for n is equal to k, that is 1 square plus 2 square plus 3 square plus etc. plus k square is equivalent to k multiplied by k plus 1 multiplied by 2k plus 1, the whole thing divided by 6. We shall now prove that P of k plus 1 is also true, that is, we have to prove 1 square plus 2 square plus 3 square plus etc. k square plus k plus 1 square is equivalent to the required form that has been given to us. So, for the first k terms we can write that as k multiplied by k plus 1 multiplied by 2k plus 1 divided by 6 from the assumption. Now, we have one extra k plus 1 square also that we have to add. That can be written as k multiplied by k plus 1 multiplied by 2k plus 1 plus 6 multiplied by k plus 1 the whole square divided by 6. We have taken LCM, and then that leads to k multiplied by k plus 1 multiplied by 2k square plus 7k plus 6 divided by 6, that again gives us k plus 1 multiplied by k plus 1 plus 1 multiplied by 2 multiplied by k plus 1 divided by 6. When you compare this with P of n, this is the required form that we have to have for P of k plus 1. Therefore, the P of n is true for k plus 1 also, which means according to the principle of mathematical induction, P of n is true for all the natural numbers n. Next, we shall see another definition, that is we are going to define factorial now. Factorial, the notation we are going to use is the exclamatory symbol. So, 0 factorial is defined as 1, and for any integer n greater than or equal to 1, we are going to define n factorial to be equivalent to n multiplied by n minus 1 multiplied by n minus 2 multiplied etc. up to 1. That is, you have to start from the given number, you have to decrease the product until you reach 1. That is, if 3 factorial is equal to 3 multiplied by 2 multiplied by 1. Therefore, 0 factorial is equal to 1, that as per the definition. 1 factorial is equal to 1, and 2 factorial is equal to 2 multiplied by 1. 3 factorial we have seen. 8 factorial is equal to 8 multiplied by 7 multiplied by 6 multiplied by 5 multiplied by 4 multiplied by 2 multiplied by 3 and then multiplied by 1. You have to start from 8 and you have to end with n and multiply all of them in between. That will give you 40,320 to be the value of 8 factorial. Thus, 9 factorial is equal to 9 multiplied by 8 factorial. That will give us the value of 9 factorial, that is equivalent to 3,62,880. Now, we shall see the strong version of the principle of mathematical induction. Let P of n be a statement where n is the integer satisfying the following condition. First one, P of n naught is true for some integer n naught. Second one, if P of k is true for all integers L such that n naught less than or equal to L less than k, then it is true for the integers n is equal to k, that is P of k is true. Then P of n is true for all integers n greater than or equal to n naught. The two forms of the principle of mathematical induction we discuss here differ only in the statement of the induction hypothesis. Previously, we assumed that the statement is true for just one particular integer and we had to prove it true for the next largest integer. In the strong form of mathematical induction, we assume the statement is true for all integers less than some integer and prove that the statement is true for that particular integer. The first mathematical induction we discussed seems to be the weak form which is always used. Problems requiring the strong form are seldom encountered. We conclude this session by discussing the equivalence of the two principles of mathematical induction and the well ordering principle. A set containing only one element has a smallest member, the element itself, so the well ordering principle is true for n naught is equal to 1. Now, suppose it is true for set containing k elements, that is, assume that any set containing k elements has a smallest element. Given a set S of k plus 1 elements, remove one element, name it as A. The remaining k elements have a least element, say B, and the smaller of A and B is the smallest element of S. This proves that any finite set of natural numbers has a least element. Now, we try to prove the extension of the result to arbitrary subsets of n. Conversely, we can use the well ordering principle to prove the principle of mathematical induction, that is weak form. For suppose that P is a statement involving the integer n which we wish to establish for all integers greater than or equal to some integer n naught. Assume P of n naught is true for some integer n naught. If P of k is true for arbitrary integer k greater than or equal to n naught, then it is true for the next integer P of k plus 1. How does the principle of well ordering show that P is true for all n greater than or equal to n naught? We assume that n naught is greater than or equal to 1. If P is not true for all n greater than or equal to n naught, then the set S of natural numbers n greater than or equal to n naught for which P is false is non-empty. By the well ordering principle, S has a least element, say A. Now, A is not equal to n naught because we have the statement is true for n is equal to n naught. Thus, A is greater than n naught, which implies A minus 1 is greater than or equal to n naught. But A minus 1 is less than A. So, by minimality of A, P is true for k is equal to A minus 1. By the assumption 2, P is true for k plus 1 is equal to A, which is a contradiction. We are forced to conclude that our starting assumption is false. P must be true for all integers greater than or equal to n naught. The preceding paragraphs show that the well-ordering principle and the mathematical induction weak form are equivalent. Similarly, we can also prove that the principle of induction strong form and the well-ordering principle are equivalent to one another. So, we can conclude that the three principles are equivalent. Dear learners, we have reached the end of this module. In this module, we introduced the statement of fundamental theorem of arithmetic and we learned how to represent positive integers using prime number. And then we learned a method called principle of mathematical induction, which helps us to understand how to prove statements involving natural numbers in an easiest way. I hope this session would be very useful to you. We will meet in the next session. Until then, thank you.